Yes, so our next speaker is Surinder Sud from Armour. He's a principal engineer. He's going to talk about a novel formal verification solution to non-convergence. Surinder Sud holds a PhD in design verification, validation of hybrid systems from the University of Auckland in New Zealand. He has an overall experience of 20 years. Most of the time is spent in verification of hardware components to the system on chips. He's worked on different verification techniques while verifying such design. His research interests includes formal verification of digital and hybrid systems. He's also done work in security vulnerability, verification of digital hardware, and also performance estimation of SOCs while doing its SOC verification. He's worked with many prestigious organizations like Intel, AMD, Samsung, ST Micro, and ScanDisk, and he is currently working for ARM as a principal engineer. Thank you.
Thank you. So, hi everyone. Today I'll be discussing on uh, a known problem in the formal world. Uh, as we scale up in the design, how we can converge properties. So here it goes. So as we all know that whenever we are doing formal verification, so there are three C's which are typically coming into picture. One is the completeness. So this means that whatever properties we have written, so whether they are completely verifying the design behavior or not, there is no standard state of the art technique available to guarantee that. Second is the correctness. So whatever properties we have written, whether they are really correct in terms of syntax and semantics. So we don't have any standardized technique to do that. And finally, the consistency part, which means that with every design revision, so whether the behavior of my property is consistent with regard to that design revision or not. Finally, on top of that, as we see as the design scales up, right? So the convergence is a bigger problem. So as the design scales, so the property does not conclude to be either pass or fail, and they're hanging in between, having some arbitrary bound. So these four C's typically are the challenges in the formal world, and I think every formal engineer accepts it. And the talk is about the fourth C, which is a convergence. And we have tried and we have created some solution with regard to that. And I'll be presenting in the next slide with regard to this. So the main idea is on which our solution lies is boils down to the concept of decomposition and refinement. So if we have any system level behavior, which is let's say a property P, so which is having an assumption and a guarantee. So we describe a system level behavior as a contract which consists of assumptions and guarantees. And if we want to verify the system level contract, which is actually later on transformed into a system level property, so we decompose it. So the decomposition lies in the idea of refinement, in which we say that the decomposed properties map to the component level properties of a bigger system. And if they are P1, so then this P1 is a subset of the property P, which is the system level property. And likewise, if we have another component to which the property P2 maps, so that is also a subset or equal to the property P. So this is the theoretical idea based on which we decompose the properties. And when these inequalities are satisfied, we say the properties are refining the system level property P. So the refinement, as I said, that it boils down to the concept of decomposition. And how do we decompose? I have just tried to give a brief demonstration of that. So let us say if we have a system level behavior, which says that if there is any request which is made, it will be acknowledged in 3 cycles. And here we don't have any assumptions in this context, but we have guarantees that whenever there is a request, it should have been granted within 1 to 3 cycles. And let us say, so this is decomposed into 2 arbitrary components. One is called, let's say, request manager, and other is a responder. So what we do for the request manager, we write a request manager level contract, which is P1. So it says that whenever there is a request in, after maybe 1 cycle, let's say, you will have a request out. So again, in this case, we don't have any assumptions. but we have guarantees that for every request in, the request out should be there within one clock ticks. So now on the similar side, if we have a responder, we say that whenever there is a request out, it should be having a grant generated within 1 to 2 clock cycles. So these component level behaviors for requester and manager basically refine the behavior of the system level stuff. And how do we justify it? So that is by refinement validity, wherein we say that the assumptions, the system level assumption is a combination of the component level assumptions, which is A1 and A2 in this case, and guarantees are the intersection of G1 and G2 basically. So as this previous slide shows that the component level assumptions are actually the weakening assumptions actually, because we as we move down the component, we actually weaken the assumed behavior. So that is explained in this slide. For example, if we have the original assumption as if we have request valid and we want acknowledgement to be there within, let's say, 1 to 2 clock cycles. But if we move down the from system to the component level, we say that the environment may take up to 5 cycles. And since we are relaxing the time in terms of ACK received, so this is a weaker behavior as it allows more clock cycles. Likewise, we can also weaken the assumptions using data constraints at the component level. So this means that, for example, if we have the original property wherein we say that request valid implies request data to be equal to some value, say 8 tick HFF. So we can weaken it saying that the request data should only be 7 down to 4 having some value, rest others I don't care. So this means that the components can tolerate more behavior from its environment as we go down from system to component. And this stuff is used in the concept of refinement, so which I explained, described in the previous slide. So as we move down from system to component, we strengthen the guarantees, and that is explained in this slide, wherein we say that, for instance, if we have a valid request, so if it is to be granted within, let's say, 1 to 3 clock cycles, if I want to strengthen it, so what I will be doing actually is I'll be restricting the clock cycles. So this means that the module generates to respond sooner. So and this is how I'm strengthening the guarantees as we move from system to the component level. Another example, so we have for if we have a valid request and if it is granted, so if I want to strengthen it, I can say that if there are any pending requests which are not granted, they should also be granted for every valid request. So this is how I strengthen the guarantees as I move from system to component level. So I forgot to tell that. So in this example, like when we define weakening assumptions, that is how and that is why. So this A2 in this case, or A1 in the context of requester or responder. So A1s and A2s are basically the superset of the system level assumptions. So likewise, so for guarantees, so in this context, G2, for instance, it is a subset of G actually. So based on these concepts, the solution is proposed. So what we basically do is, first of all, we specify the system level behavior as a contract. So which is just a natural language statement. And this natural language statement consists of two things. One is assumption and second is guarantees. Now, once we have specified the system level behavior, the next thing is we need to trim it down. We need to decompose it. Now, how do we decompose it? So that is just explained in the previous slide. Wherein we use the idea of refinement, assumption weakening, and guarantee strengthening. So once that decomposition is done, we translate the refinements into system Verilog assertions. We deal with the hardware world, we deal with the hardware designs, so we translate that into SVAs. But on the contrary, when you want to do the similar thing in software, we can translate those SVAs into LTL, maybe in any other software language like Python or whatever. Now we prove those assertions. We use Jasper Gold to prove those component level assertions. And since they are the decomposed behaviors, so they are kind of primitive building blocks to verify the overall system behavior, the convergence rate is faster. But This does not guarantee at the step 4 that I have verified or validated the system level property. So for that, we move to step 5. What we do in step 5 is basically we compose those SVAs in such a manner that they refine the system level behavior. So what does it mean that? So the properties P1, P2, P3, blah, 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 which we have written for the respective components, we compose them in such a manner that a system level behavior is automatically modeled. So the composition techniques in this case can be, the standard techniques like cascaded composition, synchronous composition, parallel composition, asynchronous composition, stuff like that. Now, which composition technique we'll be selecting, that depends on a lot of things. One such thing is the nature of the design. Most of the design, like CPU, for instance, they are based on, cascaded pipeline structure. So in that case, we'll use the cascaded composition. There are designs which are synchronous, fully synchronous in nature. In that case, we'll be using the synchronous parallel composition of the properties to prove the target property at hand. So likewise, based on the nature of the design, we compose the properties and we realize the system level behavior. And the last step, which deals with the composite property verification. So if we are able to prove the component properties in a specific composite manner, then it is guaranteed that they automatically model the system level behavior. So that is the idea on the basis of which the solution was developed. And we deployed this solution in many designs, one such as the system memory management unit, in which we typically deal with. So SMMU, it has basically two components. One is the TLBs or the caches, and second is, the translation units. So whenever there is any request which is coming from, any IOs or any PCA endpoints or stuff like that, if that translation is missed in the caches, then we have the translation unit using which the translation of the addresses takes place and the address is generated. So these caches behave in a similar way, the way the CPU caches work. So this design is taken as a candidate to prove the evidence that solution works well. So we have taken three properties here in this table, uh, which relates to the invalidation requests. So the first one is like any invalidation request which comes in, it also invalidates the corresponding caches. Now with regard to invalidation of the caches, so this property means that we are dealing with, the invalidation of the translation caches. Now, in SMMU, we have two kinds of translation caches. One is the configuration cache, and second is the address translation cache. So which relates to two different blocks in a translation unit of the SMMU. So when we tried with a conventional formal verification technique, we got 13% improvement with the technique at hand, which we proposed. The second category, it also similar in nature, so it gives us 21% performance improvement. Although in both the cases, the properties were not converging, but we were getting a better bound. And when we showed this bound to the designers, they were pretty satisfied and they were happy to sign off the verification. On the last case, which is the E3, so we got a design bug which was not discovered using the conventional technique, and with a marginal 2% improvement, we were able to get that bug. So another application, so there is a granule protection block in the SMMU. The responsibility of the granule protection block is to, provide certain access permissions to different types of address translations. Because SMMU deals with, certain permission levels, which are non-secure, non-secure, realm extensions, and the root permissions. So every address translation happens in certain permission zones. So just to safeguard the security aspects of the design. And when we applied our solution to the GPT block or the granule protection check block, so we got one counter example, which is shown in this table as E1. So it says that like an invalidation operation must follow all the GPC invalidations. So GPC invalidation is granule protection check invalidations. So we got a counter example with a marginal 3% improvement with this approach. And the second one in which we got, a huge 40% improvement for for all the synchronization operation, which should always follow every translation request. So this experiment suggests that the contract based refinement technique for proving properties at a higher level of scalability of designs, so that is a well suited technique and it works well. The tool used in this case, Jasper Gold, which use the proof structure app for this. And finally, I would like to conclude. So the first point, like standard properties consume more resources. So this means that you have property at hand and you're running this property for 2 days or 3 days, and you don't see any increase in the bound of the property. So in order to handle such properties, this solution fits well. And compositional system level properties are automatically proven if their corresponding component level refinement properties are proven. So that's very important line, because if you have, let us say, for a given system property, 3 component level properties and they're all proven, then I'm not much bothered about the convergence of the system level property, because a specific composition will automatically model that behavior. But on a similar note, and or at a higher note, tools like Jasper Gold or many other tools which come in the market, they automatically start converging the system level property also. So having said that, so this means that the system level convergence show me a better bound or a better convergence. So if I'm also trying to do the system level property convergence, but if you are doing good composition, then mathematically it is really not required to converge the system level property. To achieve point 2, we need to have better refinement strategy, which none of the tools support right now. So this means that if I have a system level property, I need to have holistically defined all the refinements such that I am not bothered with the convergence of the system level property. And this is what our research is about. And we are using this solution while we integrate the Jasper Gold or VC Formal kind of tools. And we are into a better suited state when we do the convergence using this. The fourth point, the system level property, if it doesn't converge with the proposed technique, it still gives us a better bound, which I have shown in as an evidence with a couple of designs. And finally, how we can make use of artificial intelligence in intelligent selection of refinement properties. So that is problem at hand, and we are dealing with it right now. I think that's it. Yeah. Thank you very much. Any questions?
We've got 2 minutes. So if there's any questions in the room, we can quickly ask questions in the room. Otherwise, we'll go to Catherine again. Actually, there's somebody else, Catherine. So in the interest of fairness, I'll let them go first. Go ahead.
Hello. Hey, Surinder. For the GPC checks, how did you decompose? Could you talk more about it? So you had something on slide 9.
Yeah.
So you were saying that you dealt with the invalidation of GPs. Yeah, the first one. So could you talk about how you decompose the invalidation check and how it helps?
So I can give you a generalized idea on this, because I don't have the decomposition details currently in the presentation. I was not allowed to do so. Apologies for that. So at a very broad level, as I said, like for example, all invalidation operations must follow GPC invalidations, or any synchronization operation must not overtake translation faults. So let's take the second one. So let's say you are having 2 operations going in. One is synchronization, other is invalidation. So the specification says that first your invalidation should go and then the sync operation should go. Now the problem is invalidation to a bigger block, so that's not possible. So we break down the invalidation such that the invalidation is broken down into config invalidations or translation invalidations. So we do the config invalidations for the configuration block and translation invalidations for the translation block. They are synchronous in nature. Once that is achieved, we check my overall invalidation has happened or not. If that has happened, then that is a trigger for the synchronization operation, which is a synchronization barrier instruction. And this is how the synchronous and cascading properties come into existence, and the overall behavior is verified.
Okay, if you want more details, I suggest you follow up at the end. And sorry, Katerina, we've run out. You can see people moving between speakers, so we do have to stay on time. So Katerina may have a question as well. We'll go after the next speaker. We're going to lunch anyway, so I know Surinder is going to stay here. So thank you very much, Mr. Surinder. We'll move